Hello, the following video is a recorded presentation on our recent paper, Bregman style online convex optimization with energy harvesting constraints. The authors include me, Kamiyara Askari, third-year electrical engineering PhD student at USC, and my advisor Michael J. Neely, full professor at electrical engineering department at USC. Before jumping into our problem setting, we need to know about online convex optimization problem, which has an old and well-discussed setup. This problem is a sequential decision-making problem where a player makes decisions and the environment, which may even act as an adversary, chooses a loss function, and then the player suffers a loss equal to the value of the loss function at the decision point. This is a convex problem, meaning that the decision set is convex. Also, the loss function at each time slot should be convex. As it is portrayed in this slide, the game starts at time t equal to 1, when the player and the adversary should make their decision at the same time. Next, player suffers the loss, and also observe the first loss function which he will use to make his next decision. The first decision was made without any knowledge. However, for the second one, the player knows the first loss function and he can use it. And again, the player suffers the loss, the L2, regarding his second decision, and observe the second loss function, the whole function, without forgetting the first one. He will keep remembering the loss function and use them for future decision making. It should have crossed your mind that minimizing the total loss seems impossible, as the adversary can choose however he wants. So, what is a good metric to judge our decision-making algorithm? Regret. As a framework is a game theoretic and the nature of the problem is adversarial, the appropriate performance metric also comes from the game theory. Define the regret of the decision maker to be the difference between the total loss she has incurred and that of the best fixed decision in hindsight. In OCO, we are usually interested in an upper bound on the worst case regret of an algorithm. Another way, and let's look at the formulation. As you can see, there is a x star, which is equal to the fixed decision, minimizes the from the beginning to the end sequence of the loss functions, all weighted the same. And this x star goes into the regret formula to make sure that our algorithm has made a good decision regarding any fixed decision. Now, another way to look at the regret is to consider there is a second player who has chosen a fixed point at the beginning of the game. This second player is the same person as the adversary, and his objective is to minimize his total loss difference with the first players. Notice that in order to have a mathematically correct problem, decision set should not change with time, so it can chooses the x star at all times. So x star should be able to be inside all the decision sets at all time. Like as you can see here, decision set is considered to be constant with time. The next 4 slides are trying to demonstrate our paper's problem setup by building upon the OCO. In this problem, there is a system with n subsystems. The player's task is to assign the limited available energy to each subsystems. The total energy delivered to the system at each time slot should not exceed the constant given, A max. Obviously, the energy also cannot be negative, so these constraints are shown mathematically in the picture. The total energy delivered to the system at each time slot should not exceed the limited energy available to the system. However, there is a big problem. Here, the limited energy is time varying. This time varying property is basically denying us from using the regret definition, as you can see in the picture. If you remember, just get over from it. We will deal with this problem later by coming up with another idea. Let's add the last compartment of the setup and make sure that we are all on the same page. The energy source and the battery are the compartment that are extra added to OCO to make our own type of problem, energy harvesting. The energy source gives us a random IID amount of energy at each time slot, which can be imagined as a solar cell. Notice that the player do not have access to the distribution that governs the energy of the random source. Also, a battery with capacity Bmax is provided to store the unused energy or provide extra energy to be combined with the arriving energy and used to feed the system. As you can see in the picture, the player receives two sources of energy and uses them to feed the systems from N to 1. The update rule of the battery is simply just putting the remaining energy that we have received back into the battery if there is any, and if there is not, nothing. Now let's go back to the pure OCO problem. Let's look at the most common algorithm to deal with it, which gives us the guaranteed upper bound on the worst case regret. Online mirror descent. Now, I'm not trying to get into the details of online mirror descent, as it is by itself a complete 2 or 3 lectures. But if you look at the slides, it's pretty easy to understand how it works. The update rule is similar to gradient descent. There is a linear approximation of the loss function, LT, at the decision point, XT, plus the D function, which is a nonlinear convex curvature function, and adding this to the linear term causes us to have a convex optimization instead of linear. D function should have some characteristics, and any function that has those characteristics is called the Bregman divergence. In a regular gradient descent, the Bregman divergence is equal to half of the Euclidean distance of the next point and the current point. In multiplicative weight update, the Bregman divergence is negative entropy. Just look at the two definitions of Bregman at the bottom of the page. Now let's focus on a special case of online mirror descent, online gradient descent, on one-dimensional closed interval. This special case is very easy and solvable, and we will use it in our algorithm. Notice that A and B at the end of the update rule meaning that we have a projection on that interval, meaning that if it's larger than b, we're going to use b as at plus 1, and if it's less than a, we're going to use a as at plus 1. Let's try to achieve the simplified rule in the multiplicative weight update on probability simplex. This can be a little seems unfamiliar for most of the people if you look at the main optimization. However, if you look at the simplified update rule, it becomes way easier to understand. Just look at the fraction. At top we have pt, the ith element, multiplied by exponential of the term that is regarding to the gradient over the sum of all of the terms. So let's look at the next slide. Let's try to achieve the simplified rule by first ignoring the probability simplex and just take a derivative and solve the convex optimization. As you can see, it's just like p tilde t plus 1 equal to like something. It's very similar to gradient descent. Now, if we want to enforce the probability simplex, the simplest way is just dividing it by the sum of the terms. Now, I didn't give any explanation why, but this is how it works, and it's also easy to see why it works. Now we are gonna talk about, from here we will use two ideas to combine previous two algorithms that we talked about, and we will solve the OCO problem with energy constraint. The decision vector x consists of positive elements, so we can write it as a probability vector times a positive constant. The probability vector is called direction, and the positive constant is called amplitude. This is not a very common notation. Basically, we came up with it. As you can see, the p of t is equal to 1 over n uniformly if the x is completely equal to 0. So if x of t is equal to 0 at some point, we're gonna choose p of t equal to a uniform distribution. Now, remember the update rule for the gradient descent on a closed interval? We're going to use it for the amplitude. Let's combine these two. As you can see, only the derivative terms is different from what we have already seen. Like you can see, the derivative is the partial gradient of the loss function at xt regard a. And look at the projection intervals, and the amplitude can go down to 0, and it cannot pass the A max, the maximum output energy, and BT plus ET plus 1, which is the available energy for us. Next, combine the multiplicative weight update on probability simplex with the idea of separating amplitude and direction. Again, only the derivative term is different from what we have already seen. The derivatives are shown here, are not mathematically correct. We do not use them in this paper. We only use the update rule and show that they satisfy their regret bound. However, these terms are good for understanding the algorithm. Now again, if you look at the terms, you can see basically we just used the gradient of the L of t xt regarding p and just put it back in this update rule that we have derived previously. Again, let's go back to our main concern. As we have already discussed, the regret definition needs to have a constant set to choose from. However, our decision set changes regarding time because of energy availability. We will battle this situation by adding a linear term called drift to the update rule of the amplitude. This term acts similar to a Lagrange multiplier. The idea is, instead of having the term in the decision set, which causes an extra projection, we enforce it by adding a term to the update rule. However, the downside is we have an extra condition on the battery capacity, Bmax. Just look at the term. We previously didn't have this term, and now we have it. This term is responsible to make sure we don't use too much. As you can see, BT is smaller than Bmax because BT is the amount of energy in the battery, Bmax is the capacity, and this is a negative term always, and pushes us from using less and less from the battery. Less amplitude means using less from the battery. Now, if we do this, we have proven in the paper that 80 plus 1 from the up formula is equal to 80 plus 1 from the lower formula. So basically, we can ignore the time varying condition. So basically, we just don't need to remember or don't need to consider that our set of decision is changing, which is the main concern we had from the beginning, and it's solved. Now, the main algorithm, a little simplified from the paper, is here. The main two condition are given A max and B max. Parameters eta, alpha, theta, and B0, P1, and A1. Initial condition, initial decisions. We do the update rule, divide xt, and everything is straightforward. Now, after regret analyzing, which became available by using the drift term, we proved that in the paper that the regret can be bounded by a function of order square root t log n. The improvement from square root n to square root log n comes from using the mirror descent with negative entropy, Bregman divergence. The square root n was previously proven in our previous work of Michael Neely and his other student. Thank you, and you can look at the references at the end of the paper.